Welcome to a critical video by Phi Guy Francois about critical angles. So let's jump into it so we can make this nice and short, as we are critically acclaimed. So critical angles, we have to know what they are. So first we just start off by talking about refraction. So if we look at refraction, we have a light beam that's coming in, and part of that light beam will be reflected back down if it hits a surface boundary, and part of that light beam will be refracted out into the air at a certain angle. For when you are in denser materials, such as going from water into air, you have a higher index of refraction down below and a lower index of refraction up above. The consequence of this is that any angle that we have relative to this normal line that we come in with in the denser material will be extended, exacerbated, multiplied by a certain factor and come out the other side. So much so that as we increase this angle from normal, going from 0 all the way towards 90, but not actually reaching 90, our angle up on the top will bend and bend and bend until it reaches a certain point, at which point the refraction will be parallel to the surface. Past this point, you enter something known as the total internal reflection area, where you will only get a reflected ray. You will not have any refraction into the other medium. This is used for things such as fiber optic cables, which pass the data back and forth at amazingly fast speeds, faster than anything that could be supplied by, say, DSL, or cable for that matter. We do have an unshown reflection in this picture here, but this angle here that produces this 90-degree turn is a critical angle. So it is the point at which light will refract parallel to the surface, 90 degrees. So in essence, you will not see this beam, but it will be the point between where you see a refraction coming out and when you see no refraction whatsoever. That would be what you would see visually. So let's take a problem for this. So a light beam that originates in water, and I give you the index of refraction here, that's actually 1 to 3s, but we'll go with it, would emerge into air with another index of refraction. Determine the angle range where light would only reflect and not refract. So what they're talking about right here is we're trying to find out what is the area where we get this total internal reflection. So let's go to our solution. Well, we said that the range of total internal reflection is any angle between the critical angle and 90 degrees. Now, if we state the other values that were given inside the problem, we've got our index of refraction for the incident side, aka the water side, is 1.333. The index of refraction for our transmitted side, the air, is 1.000, and our transmitted angle must therefore be 90 degrees because of what a critical angle actually is. So if we take our Snell's law and we put in these values and solve for our angle. I don't go through it step by step in this one because I wanted to go a little bit faster, but if we don't put the values in actually and just solve for it, we end up with the inverse sine of the index of refraction that's being transmitted divided by the index of refraction of the incident side times the sine of our transmitted angle, which happens to be the 90 degrees. If we then plug in our values for this, we get the following equation, which when we solve it out comes out to being 48.61 degrees from the normal, and the range of total internal reflection must therefore occur between this and 90, and that would be the way to solve this problem. Have a great rest of your day, and don't be too critical of other people.